Dear colleagues, my name is Maksut Maksutoğlu and I am working at Gebze Technical University in Turkey. Currently, I am conducting my postdoctoral research on magnon and microwave photon-based hybrid quantum systems with the group of Professor Affronte at University of Modena and Reggio Emilia in Italy. In this study, I would like to present some of our recent results on coherent and dissipative coupling between inverse anapole resonator and ferromagnetic magnons. In my presentation, I will briefly concern hybrid quantum systems and I will show examples of HQS based on magnonic systems. Later, I will mention the design used in this work. This is so-called inverse anapole resonator structure. Later, I will present the results of our experimental and theoretical simulation of inverse anapole resonator with the Yttrium Iron Garnet system. Finally, I will make conclusion on our study. Hybrid quantum systems have recently gained importance due to their great potential for various applications in quantum computation and communication systems. Several hybrid quantum concepts had been proposed in literature, but all of them are based on strong coupling regime of at least two various physical substances, which they can be optical cavities, Rydberg atoms, superconducting qubits, microwave resonators, mechanical resonators, nuclear and electronic spin ensembles. In addition to these systems, in the last few years, coupling between collective spin excitations, which is called magnons, and microwave photons have gained a great attraction due to their strong coupling rates. Among various systems, a hybrid quantum system based on the combination of a microwave resonator and magnonic materials is at the focus of our study. An important advantage of the magnonic system is the possibility to tune its frequency in the gigahertz range by a DC magnetic field. A number of magnonic materials based concepts have been studied, and the dynamic of these systems are usually defined by Landau-Lifshitz-Gilbert equation. Among magnonic materials, ferromagnetic Yttrium Iron Garnet is preferred due to its low damping parameter and decay rate, while first studies concentrated on three-dimensional microwave resonators. Recently, the planar structures coupled to YIG crystal have gained growing interest. We can integrate Yttrium Iron Garnet in two different microwave architectures, investigating different coupling regimes achievable. In particular, we are selecting both superconducting resonator and metallic ones. We focus on a non-conventional superconductor, which is YBCO on sapphire and silver on sapphire substrates. You can also take a look to these previous works for further details about the general characteristics of the resonator materials. In hybrid quantum systems, the coupling strength is defined by the Rabi frequency, and the coupling regimes are divided into four according to the intensity of Rabi frequency. When the Rabi frequency is smaller than the internal decays of the excitations, the coupling becomes weak. And when the Rabi frequency is larger than the decays of photon or the material modes, the dynamics of the system dominated by the Polariton mode, and the coupling becomes in strong coupling regime. When we start to compare the Rabi frequency with the base excitation frequency instead of the decay rates of the excitations, we are reaching to ultra strong coupling regime, and the condition for obtaining the ultra strong coupling regime is the Rabi frequency should be at least 10% of the excitation frequency. And when we increase the Rabi frequency over the excitation frequency, we are reaching to deep strong coupling regime. Superconducting inverse anapole resonator structure is obtained by creating a 50 ohm microstrip on a 10 by 10 substrate with YBCO coating on both sides, and then inverse anapole resonator pattern on another 8 by 5 millimeter substrate with YBCO coating just on the one side. The hybrid structure is obtained by placing the inverse anapole resonator chip on top of the microstrip. All of the geometric parameters are optimized by taking account the field distributions, resonant frequencies, and quality factors of the modes by using the CST Studio Suite. And we obtained two main resonant modes, which they are occurred by the coupling between microstrip. And in terms of the quality factors, the first mode has around 500, and the second mode at 14 GHz, and it has 700 quality factors in simulations. And we obtained very localized concentrate magnetic field, microwave magnetic fields around the outer conducting region for the first mode, and for the second mode around 14 GHz we obtained the concentrated magnetic field, the microwave magnetic field around the central conducting region. We fabricated the resonator by using optical lithography and etching, and we placed an irregular shape of YIG crystal with the edges less than 1 millimeter. The external magnetic field is applied along the microstrip direction. The loaded quality factors of the resonator structure obtained by fitting the transmission spectrum with input-output formalism as like seen in the table. We fitted the experimental data using by input-output model, which has been previously developed by the group of Professor Affronte for the dual-mode resonator with multiple spin modes. The model involves two different photonic modes, which are shown as horizontal lines, coupled up to 3 magnetic modes, and each of them can couple to the both resonant modes through its corresponding coupling rates, and all modes are characterized by their frequencies and the coupling rates. The magnetic energies of the energies of magnetic modes obtained by using Kittel equation for uniform magnetic resonance. The other energies are found by simply adding an additional shift on the FMR mode. The fitted coupling parameters are shown in the table, and the line width of the magnetic modes are also obtained around 10 MHz. And as expected from the field distribution map, the coupling between inverse anapole resonator and Yttrium Iron Garnet is occurred just between 8.8 and 13.8 GHz modes. We are in the strong coupling regime, and the condition for ultra strong coupling regime is being approached by the magnetic mode A and for the 13.8 GHz mode. We moved the sample in the same orientation with respect to the applied magnetic field and repeated the same measurement and the same analysis, and we obtained similar results with the previous position. In this case, just two different magnetic modes coupled to the photonic modes, Besides the strong coupling in both positions, the high-order magnetostatic modes are also excited. The metallic inverse anapole resonator structure obtained by patterning the geometry on the grounding plane of the broadband microstrip. Design and coupling studies with YIG thin film performed by using CST Studio Suite by defining the Yttrium Iron Garnet as a gyrotropic material. The typical inverse anapole resonator pattern is modified to obtain two equally resonant modes by making circular gaps around the central conducting region. Even though the obtained quality factors are relatively small when compared to the superconducting resonators, this type of resonator have advantage in terms of filling factors of microwave magnetic field through the magnetic medium. When we look to the field distribution on the resonant frequencies, for the first mode we obtain with similar distribution to the superconducting resonators. For the first mode, the magnetic field distribution localized around the outer conducting region, while the second mode, the magnetic field distribution does not localized anymore at the central conducting region. It spreads all around the conducting edges of the pattern, and there is also a small absorption peak, which is not so important for the study. In coupling simulation studies of silver inverse anapole resonator structure with thin film, we used 1 by 1 millimeter in width and 5 micrometer in thickness YIG thin film placed to the center of the resonator. The line width of the YIG film defined slightly larger than the literature value for decreasing the computation time. As it's seen on the transmission coefficient map, in this configuration, we obtained strong coherent coupling between the second resonant mode and the magnonic modes, and the formation of the dissipative coupling with the first mode of the resonator also obtained. When we look closer to the dissipative coupling region, we see also the formation of the magnetostatic modes and the successive coupling of the modes with the first resonant mode of the resonator. And we also see at the resonant frequencies the exceptional points which the transmission goes to zero with very narrow line width. And when we look to the time domain animation of Z component of microwave magnetic field at the multimode resonant frequency, we see the oscillations of magnetic mode and the resonator mode becomes coherent at the exceptional points of the spectrum. In conclusions and outlooks, planar geometry of inverse anapole resonator can excite magnetostatic modes and strongly couples to magnons of yttrium iron garnet. Depending on the geometric parameters, the inverse anapole resonators can operate in a very wide frequency range and multimode photon-magnon coupling can be obtained. In this context, our study has revealed that the inverse anapole resonator structure can be used with high efficiency in quantum technology research, giving a possibility to construct a hybrid system with ultra-strong photon-magnon coupling strengths. Such architectures might offer a good testbed also for studying microwave to optical conversion. I would like to acknowledge to the support of NATO's Science for Peace and Security program and also for scholarship program to TÜBİTAK. And I also would like to thank all of my co-authors and thank you for your attention.